For those who are using a Word version, I just uploaded the Word version of this lecture. You're welcome. Okay, good morning all. Today is the second part of the Generalized Linear Models lecture. I would also, guys, attention please. I would also like to warn you, there are still a couple people who haven't sent me any emails regarding enrollment for the exam. I am going to send the form after this lecture, so if I send you an email and you haven't replied back yet, do it now. Because otherwise you may not be able to enter the exam. Okay, for today we have three things to do. The first is just to keep working on the generalized linear model assignments, because yesterday all we did was just pick the distribution and then fit the model. Today we're going to go one step further with the same exercises, and then I will discuss the solutions to the linear regression assignment, the model selection one, and if we have time left I will also explain how you can get the results of a generalized linear model from the output. So, yesterday we talked about why you would use a generalized linear model. In essence, it's just to perform regression where the outcome is not conditionally normally distributed, but you do have an idea of what kind of data it is. So, is it counts? Then you could use a Poisson distribution. Is it some sort of ratio, binary data, or hidden ratio? Then you can use a binomial distribution. Now, that's we can do with a GLM. And today we're going to talk about what a GLM actually is, and that is a three-part model, so I'm going to explain what those three parts are. So the three parts that make up a GLM are called the error structure, which just means the distribution for the errors. The linear parts, which is very similar to what you've already had for linear regression, and the link function, which connects the two. Okay, so as an example, we could have a normal error structure that would be the same as just doing linear regression. We could have a Poisson error structure for counts and a binomial error structure for ratios. The linear part, it explains the linear relationship between the explanatory variables and something we call eta, because we're not explaining the outcome, but we're explaining the expected outcome after performing some transformation, and that transformation is called the link function, which translates the linear part to the expected value of the outcome. Okay, so here's an example of a distribution that is definitely not normal. This is the Poisson distribution, the distribution of independent counts. And you can see from this animation that when the mean, lambda, is close to 0, then the probability gets pressed into the side and it gets more and more right skewed. So it has a much longer right tail than a left tail. Now, this is one of the probability distributions in the exponential dispersion family. So this is one of the distributions we can use in the GLM. And that makes up the first part of our GLM. It's error structure, in this case Poisson. So the error structure is a sensible choice for the probability distribution of your outcome after you've taken into account the effects of the explanatory variables. And also it's the whole reason we're using a GLM, because everything else we could already do with linear regression. The linear part explains how the explanatory variables affect the mean of the error structure. Now that sounds a bit complicated, but the only reason I'm saying it is because the outcome doesn't have to be normally distributed. So it could be the mean for a normal distribution, but it could also be that it relates to lambda for the Poisson distribution, or that it relates to n and p for the binomial distribution. It works exactly the same as what you've learned for linear regression so far. So you can do GLMs with simple linear regression, you can do it with multiple linear regression, you can add dummy variables for factors, and you can add interaction. That all works identical. So this is what that looks like. We're explaining something called eta, and that eta we're going to translate with the link function to the error structure. But this part is really, you've already seen this many times. This is intercept plus slope times explanatory variable for simple linear regression. And for multiple linear regression, just add more terms. So here's another slope and another explanatory variable. So that's the only thing that's really changed. Now, the link function is the transformation that translates from the linear part to the expectation of the error structure. It doesn't have to necessarily translate to the mean, but that's something I'll explain all the way at the end. What it does do is it is very similar to transforming your outcome variable, but applying a transformation to the outcome has certain problems that are a bit beyond this course, but just take my word for it that a GLM is a better solution to it, because if you are translating the expectation, that's like only translating the systematic part, and you're leaving the errors untouched, and those you can just give a sensible choice of a probability distribution, so normal, Poisson, or binomial. When you transform your outcome, you are ignoring the fact that there is error in your outcome. So you are also transforming the error, and that makes it really difficult to get good estimates on the original scale. And the GLM doesn't have that problem. Okay, so what is the link function? For counts, there is a link function called the logarithm, and the reason for doing that is that you're kind of stretching out the early part of the distribution and squeezing the later part of the distribution, such that it is more symmetric and such that the mean actually corresponds to, the thing that is more or less at the top, the mode. So yeah, we can see what that looks like for different values of lambda. So here at the top, I've shown the actual Poisson distribution, and at the bottom, the Poisson distribution with a logarithmic transformation applied. And you can see that this one becomes symmetric much faster and is essentially already symmetric when lambda is really, really small, whereas the top one keeps having this long right tail unless you get really, really high counts on average. Yeah, so this is the Poisson distribution. This is the Poisson distribution after applying a logarithmic transformation. This one has strong right skew until we are all the way in the hundreds of counts, and this one doesn't have right skew. Okay, so another reason we're using the logarithmic transformation is because it has an interpretation in terms of multiplicity. When you don't apply any transformation, then the difference between counting something once or twice is the same magnitude as the difference between counting something 20 times and 21 times, or 100 times and 101 times. But when you think intuitively about counts, that doesn't make sense, right? The difference between having 1 or 2 apples is much bigger than the difference between having 100 and 101 apples. So applying a logarithmic transformation is like saying the difference between 1 and 2 apples is more like the difference between having 10 and 20 apples, or between 100 and 200 apples, which makes more sense because when we think about counts, we are more interested in smaller differences than we are in the differences for very large counts. Okay, here's then a complete example using all three parts. So the error structure, Poisson distribution, the linear part, this is just a multiple linear regression with two slopes, x1 and x2. And we have the link function, which this means expectation. So the mean of the outcome is the logarithm of this linear part eta. And that's it. That's a GLM. So what does it look like in R? You specify you want a generalized linear model, GLM, and then you give the outcome as a function of explanatory variables. You then tell R what distribution you want to use, so Poisson distribution. And if you do that like this, and you open a bracket, you can also specify the link function. Now, something I didn't explain yesterday, to keep it simple and to just first get across the point of using a GLM, is that we can specify this link function. If you don't do that, if you do this, then it will use the default, which is the canonical link function, which I will come back to later, but that's like the first choice for link function you would usually use. So if you just specify this, it will use the logarithm for Poisson. Now, but there are other link functions. So that's the assignment for today. The exercise from yesterday, we had different kinds of GLMs that you could fit. You had to choose the right GLM and try and change the link function. Try and change Poisson to Poisson with square root as a link function, for example, and see which of those produces a better fit. The way to do that is to fit both models, one with logarithm, one with square root, and then maybe compare their AIC, maybe compare their BIC, etc. Okay, for binary data and ratios, it would be a binomial distribution as error structure, and then the linear part could look exactly the same. It's still just a linear model. And the link function is a bit more complex. It looks like this. It is the logarithm of something divided by 1 minus something. Now that's called the log odds or logit. And I will explain a couple slides from now with a figure why we use this transformation, because the first time you see it, you're probably like, okay, why? But actually, when you see what we're doing here, it makes perfect sense. So what this one looks like is you specify a GLM outcome as a function of explanatory variables, and then as family you specify that you want the binomial distribution, and as link function logit. Now this is the canonical link function for the binomial distribution, so it's the same as not specifying anything, it's just the default. But again, there are other options. So also for binomial models, you could try using a different link function and seeing if you get a better fit. Yeah, so one example is the probit link function, another is the complementary logarithm. You don't have to know what those look like or why they might be better for the purpose of this course, but just be aware that there are different link functions you could use because there are different ways to squeeze numbers and stretch them out such that it looks more or less symmetric. Now, why do we use the logit? The logit is when you take the logarithm of something, what happens is if you only have positive numbers, so from 0 to infinite, then what you're really doing is you're stretching it out to from minus infinity to plus infinity. So what does the inside part do? The odds. Let's say that you have a chance, you have a probability, and you divide that by 1 minus that probability. Then instead of having a number between 0 and 1, you now have a number between 0 and infinite. Now, combining those two, so having a number between 0 and infinite from the odds, and from infinite to minus infinity to plus infinity from the log odds, then suddenly we have this nice continuous scale, and we can use linear regression much more effectively. An intuitive way to think about it is that the difference between 1 and 2% is probably a lot more interesting than the difference between 25 and 26%, right? Because that's a twofold difference. The same goes at the other end of the spectrum. So a difference between 98% and 99% is much more important than the difference between 50 and 51%, for example. So somehow we want to stretch out both the part near 0 and the part near 1. Now, what happens when you take the logit? Then the difference is about the same every time you double in terms of the chance of something occurring. So 1 to 2 is about the same difference as 2 to 4, and 5 to 10 is about the same difference, and 10 to 20, 25 to 50, etc. And when we get to the other end of the scale, the same thing happens. Going from 50 to 75 is about the same step as this, as this, as this, as this. So in other words, we're thinking in terms of a doubling of a chance or a halving of a chance, which is a much nicer interpretation than a linear model, which would just say, okay, we go from 0 to 1, and after that it's 101% and 102%, 150%. That doesn't exist. There's no chance greater than 100%. So by doing this transformation, yeah, we get numbers that can be negative, -4, or positive, +4, and as we get to 99.999, it's still just a number. It's still just 6 or 7. Yeah, so this way we can also compare really small numbers, like the difference between cancer incidence for two different groups. You know, if it's a rare type of cancer, it's not going to happen very often. So it could be the difference between 0.1% and 0.01%. Now that difference with linear regression you're not going to pick up, but when you apply the logit and you use a GLM, then actually that is seen as a 10 times difference, right? Because it's a one decimal separator next, so that's a 10 times larger chance. So that's why we applied this transformation. Any questions about this? Okay. Now, what I just talked about is called the canonical link function. So I just told you there's different ways you could stretch numbers, right? We can apply any kind of transformation we can think of, but there's only one transformation that translates exactly to the mean of the outcome. That one is called canonical. Now, there is only one canonical link function for every probability distribution. For the normal distribution, it's doing nothing, which is why you don't need a GLM for a normal distribution. You could just use a linear model. For binary data and ratios, it's called the logit, and for count data, it's the logarithm. Now, these two are the only ones you have to remember. There are also other ones like the gamma distribution as canonical function, the inverse, but you don't have to remember those. Only for counts and for ratios, I want you to learn how you can model it and why that might work. Okay, but these are canonical, but as I just showed you, there are alternatives, so give those a try and see if they produce a better fit. So that brings me already to the exercise of today, which is to keep working on the exercise of yesterday and the day before, if you haven't finished those yet. Then we're going to try to fit the models that you had yesterday using different link functions, and see if it makes any difference, if you get different estimates, if you get different p-values, and if you get a different AIC value. And then at 11:30, so we have about 2 hours to do that, we will have the second lecture, and that's not really a lecture, but I will give a demonstration. So I will go over some of the answers, and you can tell me which ones you found difficult, and we'll go over the complete analysis. And it's easiest to show you how to interpret things while you're looking at it. So while we're doing that, I'll explain how you can actually interpret the output of everything in the GLM summary. Yeah, and if we have time left, I'll show you how to transform your estimates to the original scale. So maybe you did a binomial GLM and you want an answer in percentages, that can be done. And maybe you want to plot your model, that can of course always be done. So if we have time left, I'll show that. If you don't have time left, I will upload to Brightspace how you can do that, and Harold will also show it tomorrow. So that's the important part of today, understanding what a GLM is, a three-part model, so error structure, linear equation, and a link function, and understanding what the purpose of this link function is, because what the reason for using a different distribution is we already discussed yesterday, and what the linear equation is you already learned last week. So was it clear up till here? a little bit? Okay, just give the exercise a try, and then we will reconvene at 11:30.